Hello everyone, this is Shrikant, and today we're talking about deep learning and implementing CNN. So let's go ahead. Hey, hi everyone. So today we're working on recognizing handwritten digits using convolution neural networks. And for the purpose of this project, I'm using an MNIST dataset, which is a Hello World dataset for deep learning projects. So MNIST is Modified National Institute of Technology. So MNIST is a Modified National Institute for Standards and Technology database. So MNIST is a Modified National Institute for Standards and Technology database. So it contains different formats that human writes digits in from 0 to 9. So if you look at the picture here, so it gives us a different formats on how we might write a letter, a number 0. So and then number 1, 2, 3, 4, 5, 6, 7, 8, 9. So it contains about 60,000 training images and 10,000 testing images, which are in a 28 by 28 pixel format. Since they are in 28 by 28 pixel format, we can represent them as a matrix as shown below here. For number 1, anything that's closer to the number 1 can be represented by the pixel is given by 1, and which is towards the edges is represented by something that's less than 1, depending upon how close it's towards the 1. So it can be a 0.8, 0.6, or 0.1, which is really at the rear end. So once you have this 28 by 28 matrix, you can represent that as a 784 dimensional vector, since you have 784 different numbers in here. So as we have discussed a little bit about this database now, let's see how we can predict these numbers. So our problem statement here is to predict the handwritten digit using CNN. So we want to give all these training images and test this using the testing images that we have. So we're going to use 60,000 training images that we have, and we are going to test on the 10,000 testing images. So we are going to be using CNN for this. So let's talk in a brief about what CNN is and what's the architecture of the CNN. So CNN has different layers. So in general, so if you consider this architecture that we have, which is predicting an image of a car, so CNNs are usually used for predicting for image recognition. So if you see here, so let's say the first layer is a convolution layer, and then a rectified linear unit, and then a pooling, and then a flattening, and fully connected and softmax. So a convolution layer is something that extracts the features out of an image. So if you consider this particular figure, so for a car, anything from a headlight to tire to windshield or a side mirror can be a feature which is being extracted in a convolution layer, and then we are going to pool them. So pooling is something we're going to reduce the dimension of the matrix so that your system will have much less computational time, and then we're going to be going with the rectifier unit to introduce nonlinearity, and they're going to flattening and fully connected and sigmoid function using a softmax activation function at the end to actually give you the result. If you look at in detail about what we're doing for handwritten digits, so let's take 2 as an example here. For 2, we can say the bend here is a feature, the loop here is a feature, the extra line here is a feature. So all these features are being extracted using the convolution layer, and then we're going to pool them. So that's what happens. So when you give an input of this image to a convolution layer, so this is being extracted here as a feature. The next coming to is pooling. In pooling, what the model does is, so it's going to pool the matrix. So let's say if you have a 4 by 4 matrix and you are trying to pool a 2 by 2 grid here. So in this 2 by 2 grid, if you're doing max pooling, so in pooling you have 2 different forms of pooling, which is max pooling and average pooling. If you're going with max pooling, then in this 2 by 2 grid, the system is going to take the maximum number, which is 9, and then represent this 2 by 2 grid with a single number here, which is 9. The same way, when you're going with average pooling, it's going to take a summation of this and do an average, which 16 by 4 is 4, and then it is going to replace this 2 by 2 grid with 4. For the next step, it's going to go ahead and do the flattening, which is it's going to flatten this matrix into a single dimensional vector. So this is how it's going to happen. All the rows are going to become columns. So 1 0 0 4 2 1 0 2 1. The next one is a ReLU, a rectified linear unit. A rectified linear unit is something that will introduce a non-linearity to our model. So with respect to handwritten digits, how we are going to working with ReLU is to make anything that's less than 0 as 0. So anything that's minus 249, minus 91, minus 37 is going to become 0 except for the positive numbers. And the end comes the softmax layer where we are going to apply the activation function to get the probabilities of what that number might be based on the 10 different classification that we have. So once you submit the output from the ReLU to the sigma activation function, it will generate different probabilities as given here. So if you consider this this particular example where we are considering 2 as our input, so at the end you will end up with a higher probability for 2 because it's actually 2, and since the features of 2 are a little bit towards the 3 as well, so this particular loop until here is going to be 3 where you're going to just extend it like this. So it might end up with a little bit higher probability for 3 to just 5% compared to 4, which is just 1%. At the end, whichever has got the highest probability will be selected and given as an output. So for this particular one, 2 will be the output. Now let's talk about implementing that using Python. So here I'm using TensorFlow and Matplotlib to plot the different images that we have. I'm using MNIST dataset from the inbuilt Keras datasets. I'm converting that, splitting that into train and test. I'm loading them into respective objects. I just wanted to visualize and see how the images would look like when you visualize. I'm using Matplotlib, so I have visualized one of them, which is 204 and 6. That's how it looks like. Next, I'm converting the three-dimensional NumPy arrays into 4 dimensions, and I'm converting them into floating point as well. Now I'm normalizing the dataset using and by dividing it by 255 since there's a maximum RGB code. And now let's come to the convolutional model that we have. I'm using a sequential model and I'm adding a convolution layer, max pooling layer. I'm flattening it. I'm using a rectified linear unit, and then I'm using a softmax function. Once I have developed the model, I'm compiling the model, and so I'm using Tenebox to fit the model. I'm using accuracy as a measure, accuracy and loss as a measure. So if you see with Tenebox, I've got a pretty good accuracy of 99.37. I'm evaluating the model going further using test data set that we have, which is um, X test and Y test. I got a very good accuracy of 98.49. So I went and I wanted to see how this test was getting performed. Is the digit being recognized as such? So I just extracted one of the images and I'm trying to predict it. So a number 4 is being predicted as 4 here. So the same way I wanted to see if we can I can draw myself with a 28 by 28 pixel image and then ask the model to predict it. So I have drawn a couple of images. So I've drawn somewhere 15 images like this, just and then go ahead now go to the pixels and change them as 28 by 28 and then save them and give them the input to the model. So if you see all those images, 3 is being predicted as 3, 5 as 5, 2 as 2, 3 as 3, 1 as 1, 9 is a weird shape, but still it got it as 9. 8 is being predicted as 8, 4 as 4, 6 as 6, 7 as 7, a different version of 7, and then 0 as 9. So that's a wrong one, but it's no, at least 10 out of 11, which is a very good accuracy. Thank you for watching. This concludes my video on recognizing handwritten digits using convolutional neural networks.